Welcome everybody. Today we're going to look at the distance versus velocity graph again. Now we did this when we did our differential calculus, and we did those velocity, distance, acceleration sort of graphs, and so it's sort of the same stuff. It's not anything different. The only difference is before we started with our distance graph, and then we differentiated to find our velocity, and then we differentiated that again to find our acceleration. In these examples, we'll be working back the other way by taking the integrals. All right. So now I've taken this summary straight out of your textbook. It talks about the steps that you need to go through in order to find everything. Now, keeping in mind, we know that our velocity equation, when that's equal to 0, will in terms tell us where we change direction. All right. So the total distance travelled, a slightly different way of doing it in terms of thinking. If we have our velocity versus time graph, if you look at the area bound under the curve of that will in fact be one way that you can actually find the area, the total distance travelled. All right, so let's look at an example now. Just before we do that, this is the key understanding what we want you to understand. So if you've got something which is in fact the acceleration equation, and if you actually integrate that, then you get back to what we classify as the velocity. All right. So, and then if you integrate the velocity equation, you get back to the distance equation. So that's really the concept that we're looking at. We're just doing the reverse of doing the differentiation type question. A lot of the same things that we did before, we still have to do here. All right. So keep that in mind when we're going through this example from the review chapter. All right, so here's a particle that's moving with an acceleration given by that. Now the first thing that I need to do in part A is to find the velocity of the equation. So let's do that by integrating this function here. So that's going to be 2t take 3. Now if it's t, we're integrating with respect to t. So that's going to give me something like 2t squared all over 2. Now the 2's will cancel out and leave me with t squared. And then that will be take 3t, and because it's a indefinite integral, we have to put our c value in there. Now if you look at the question, there is some information up here. When t is equal to 3, we know the velocity is equal to 2. So what we could do there is go 2 is equal to 3 squared, take 3 times by 3 plus c. Now obviously that's going to cancel each other out. So therefore, in this particular case, c is equal to 2. What it means is I can now write my equation that we're going to use is v of t is equal to t squared take 3t plus 2. So that's the equation we're going to use for doing everything else in the question. All right. So now the times when the particular particle changes direction is going to be what? Well, that's going to be, it changes direction, obviously, when the velocity is equal to 0. All right, so that's the key concept that you need to understand there. Obviously, the velocity is equal to 0, so it changes direction when v of t is equal to 0. All right, so that's really what I have to do. Therefore, I can say that t squared take 3t plus 2 is equal to 0. Now, if you can't factorise that really easily, you could go and use your polysynth, but I think this one's pretty obvious what it's got to be. So it's got to be t squared, can only be 2 and 1, and because it's negative, they both have to be negative there. That's equal to 0, so therefore, t is equal to 1 or 2. Now let's do a sign diagram for this one. So a sign diagram, keeping in mind, it's a time one, so this has to be t, the smallest it can be is equal to 0 there, and then we're looking at the velocity equation. All right, so our critical points are 1 and 2. Now, if we use this diagram here, then what we can do is we can put the value, some value that's in here. So let's say put a half in there. That term's going to be negative. That term's going to be negative. So two negatives times together will be positive. Pick a value between 1 and 2, say 1.5. This term will be positive. This term's going to be negative, so that's going to give me a negative. And then pick a value greater than 2, let's say 100. That's going to be positive and positive, so therefore that's going to be positive. Alright, so we know in this particular case, in this region here, it's going to be going in the positive direction. Okay, then it changes to go into the negative direction, and then it changes to go in the positive direction. Alright, so that's the two turning points that we do have for that. In part C, it asks us to find the total distance travelled by the particle in the first 3 seconds. Now, the other thing I should point out, if we go to our graph, and if we graph this thing, then you'll see that our graph goes and it changes direction there. Alright, so that's the point, that point there being 1, and that point there being 2. That's what we're doing there. Alright, so keep that in mind. Now, the reason why it looks black is I've actually used my calculator to find the area of those things, just to check those out before I started this video. So we'll go, I'll show you how to do it on the calculator, and I'll also show you how to do this by hand. Alright, so let's do part C. So what we need to do is we need to find the distance it's travelled. So obviously the long way of doing this is to find the turning points where it changes direction. Alright, so to do that I need to find my distance. Alright, so that's going to be equal to the integral of our acceleration equation. So that's going to be t squared take 3t plus 2, and we're going to integrate with that respect to t. So then that will become equal to t cubed on 3 take 3t squared on 2 plus 2t plus our c value. Alright, so obviously the key critical points that we need to be considering is s of 0, s of 1, and then s of 2, and then s of 3. Alright, so those are the key points that we need to consider. Now the first point is going to be an easy one because that's just going to be c, because the t puts t equals 0 in there. The next one is going to be simply equal to a third plus 3 on 2 plus 2. Now, if you're not great with fractions, and that's going to be plus c, you could use your calculator. The common factor there is going to be 6. Okay, so that's going to be 2, 3 times that's going to be plus 9, and then that's going to be, to get 6 in there, it's going to be plus 12. Alright, plus c. So we could say that's equal to 23 on 6 plus c. Right, now when we're looking at 2, putting 2 in there, that's going to become 8 on 3. 2 squared is going to be 4, so that's going to be, oh, sorry, I made a mistake here, guys. So that should be take. So if we go back and change this, that's going to be take. Yeah, easy to make a mistake. That will become 12 on 2, and then that's going to become equal to plus 4 plus c. Over here, this term has to become take 9. Alright, so if I take 9 away from that, that's going to give me not a value of 23, but it's going to give me a value of 5 on 6. Okay, so that's the value I'm looking at there. Right, so just check I've done this correct. So it's 3, you've got basically it's 4, so that's 12 on there, so that's right. And then you've got 2 times 2 is 4. So this one here is 6, isn't it? Right. So really, if we're looking at that, I could simplify that and write that as simply 8. So 8 on 3 is 2 2/3. I could say that is take 6 plus 4 plus c. So that's going to give me minus 2, so that's going to give me 2/3 plus c. If I gathered that right, I think I've done that right. And then the next term over here, we're going to go over here and we're going to put the 3 in there. So that becomes 27 on 3, 3 cubed, take 27 on 2 plus 6 plus c. So that's really like 9. that basically becomes equal to take 13.5. Is that right? And then that's going to be plus 6. Alright, plus C. So that's 15, take 13.5. That's going to give me like 1.5. Alright, so that's going to be 3 on 2 plus C. So if we're doing this by hand, then we know at time t equals 0. So let's start drawing our line over here. Alright, so this is the line. So it starts at C. Okay, so this is my starting point here at C. When t is equal to 0, it's going to go forward. Okay, it's going to go to a distance of this here point here is going to be at 5 on 6 plus C, and that's at t is equal to 1. It's now going to change direction. It's going to go back that way. It's going to get to a point where the function's going to get to 2 on 3 plus C, and then it's going to change direction. Okay, so it's going in these directions here, and at t equals 3 seconds, so I'll keep going this direction here, and t equals 3 seconds, it's going to be at 3 on 2 plus C. Right? Considering it's got plus C all the time, when we start looking at the actual distance travelled, right, we can really say that the total distance travelled is equal to the first bit, which is 5 on 6. Now it's going to be this distance here, which is going to be plus 5 on 6 take 2/3, right? And then it's going to be this distance here, which is the distance between 3 on 2 and 2/3. So plus 3 on 2 take 2/3. Alright, so that will give me my total distance travelled. So again, probably making these all out of 6 would be easiest. So 5 on 6, this will become 5, that will become 4 on 6. So 5 on 6 take 4 on 6 is going to give me 1 on 6. And then the same thing over here, if we put those to become both out of 6, then that's going to become, we'll just write it down because it's probably easy if I do that for you to see. That will become times by 3, that's going to become equal to 9 on 6, take 4 on 6. Right, so then that's going to give me a value of 5 on 6 plus 1 on 6, right, plus 5 on 6. So then that will give me a total distance travelled of 11 on 6. Okay, got the idea in terms of what we're doing there? So that's the long way of doing it. There's no reason why you can't use your integral on your calculator. Alright, and I'll show you how to do that right now. So when we come to a calculator, you have an integral button on your calculator where you can go to number 7. So keeping in mind, if we put our lower limit as 0 and put our upper limit as say 1, it will work out that region, okay, this region here. So that region there is in fact 0.833. Now if you do that on our calculator, that is in fact going to be 5 on 6. Right? Now if I do the next bit, I go to my calculator, come down to number 7, right, and I do my lower limit, which is going to be equal to 1, and then do my upper limit, which is going to be 2. Then it does this area here, which is negative 1.66. Now, because that's below the axis, it's going to give you a negative value. That's equivalent to, in fact, 1 on 6. All that means is it's travelling in the negative direction. So we can't treat it as a negative. We have to treat it as a positive. And then the next bit, you go into your calculator, and you can see that if I go to number 7 again and go from 2 to 3, and I apologise that you can't see the thing moving, but I've already done it in the previous example. So in terms of that, you get the same distance, which is 5 on 6, and that matches with what we see over here, 5 on 6, 1 on 6, and 5 on 6. So that gives us our total distance travelled. Got to be careful though in terms of your calculator. If you did something like this, the integral from 0 to 3 of our v of t function, if you did that, then what you would get would be 5 on 6, take 1 on 6, plus 5 on 6. So that would give you a value of 9 on 6, which would be totally wrong. All right, get the idea? Because it's actually, that's below the axis. This bit here is below the axis, so therefore it's going to give you the wrong value. So you've got to be careful with that. So if you wanted to work out the area in your calculator, what you need to do is you need to go 0 to 1 of v of t dt, and you'd say the area is equal to, take away the area of 1 to 2 of v of t dt, plus the area of, or the integral of 2 to 3 of v of t dt. So you've got to consider whether it's above or below the axis if you're going to be doing that. So for that question, you'd have to put that into the equation like that. Now, we'll talk about why that one becomes negative in another example when we start talking about the areas under a curve. All right, so just be careful with that. That's something you need to be considering. Probably a hard example in the terms of it does go below the axis. Probably some of the other ones might change direction, but they might not go below the axis for that. All right, I hope that helps. Anyway, you've got some questions to do. If you need some help with that, make sure you catch up with me in class, and I'll talk to you later. Bye for now.